Where'd the slides go? All right, there we go. Sorry about that. So for today, administrative things, I just spoke with the preceptors, and problem sets will come back Thursday. They're graded, but they just still have to be entered. General feedback, I want to thank everyone for taking the problem set seriously and doing a good job on it. The average was right about where it needed to be. So thank you. The quiz one will be here Thursday in this room, just fill in every other seat. Normally I can say you've all taken quizzes before here, but I'm not sure that's the case right now. So every other seat. You can use calculators if you want, you won't need to, I'll tell you. Bring a couple pens or pencils, either's fine. I don't anticipate there being any pencil and paper mathematics above and beyond basic, like what's 7 + 3 level stuff, right? You'll get the quiz, you'll fill it out on the quiz, grade it, hand it in. We'll go through the procedures there, but basically if you finish when there's 10 minutes left or less, just stay in your seat till the time's done so you're not disrupting people. I'll come in with a box. We'll distribute a little before 1:30. We'll start promptly right around 1:31. We'll finish promptly at 2:21 and I'll walk out of the room with the box. Cool? Has anyone not taken a quiz here? Oh, okay, a fair number. Oh, wow, okay. It's part of the honor code is that I'm not in the room nor any of the preceptors when you're taking the quiz. We're just out in the hallway working on the solutions manual or doing like whatever we're gonna do. So not necessarily keep an eye on each other because that's weird, but it's up to you to follow the honor code in the room by yourself. I'm not here to oversee you. And that's just part of the honor code. Let's see. Anything else on the quiz? If you have any questions or problems, just send me an email and we've been responding to those in the last day or two. For those of you with ODS accommodations, there is a Google form, fill it out. Email Arancha, we're currently reserving rooms for folks with time and a half or extra time for one reason or another. We're reserving those rooms, but we'll be in touch with you specifically with all that information. Okay. Yeah, please.
Up to what lecture did quiz?
Anything related to the paper. So I guess up to the last lecture, but I didn't see much in the way of regressions on it, which means you can probably anticipate it on the next quiz. Okay, I can't promise there won't be a regression question, but if you can find a regression coefficient in there, was there one? I didn't see it. Okay, but I do want to emphasize that the quiz is being driven by what's in this paper. We're not going to come up with contrived questions to work in things from class. Okay. Precept is canceled next week. So precepts will meet again, we'll meet on Friday to start the next handout, and then they'll resume the Monday after break. Okay. We'll pass out, let's see, problem sets are coming back after Thursday after the quiz. Any other questions or anything before we get rolling? Okay. Oh, is there a question? Nope, just we freeze that entire part of the course for a week so you can focus on other courses. All right? You're welcome. Okay. So the main ideas for today. Today we're going to continue with the linear regression, where we have an outcome variable yi and an independent variable xi. Okay. We're going to begin by examining this model where there's one control variable or one predictor, xi. We'll expand it out later to adding multiple predictors and talk about that. But really, when you study statistics, you want to understand the simplest possible model before you move to the next one. That's just a general approach to these things. So we're going to spend some time with this simple model, learn the intuitions and concepts of this model, and then gradually build it out. So our assumed model, we're going to write it as yi is equal to alpha plus xi beta plus an error term. This means we're assuming that if we were to plot yi versus xi, then yi could be written as a line plus or minus some noise. And that's what the epsilon I term is. The noise determines how far above and below the line the data is, but the systematic element is the line, and that's what we're interested in. Not necessarily that epsilon term, that's just randomness or chance error. We're interested in what's the structure, what's the slope, and what's the intercept of that line. We want to take y as a function of x and model it linearly, come up with the best possible line for this approximation, and then down the line we'll do inference. Talk about whether construct confidence intervals and uncertainty intervals and that sort of thing. But for now, we're just putting a line to data, okay? The regression line should be understood as a line of best fit. This is an important idea that will carry you all the way through machine learning and high-end econometrics and all sorts of things down the line, where what we do is we say, here's how close here's how close a line is to our data. Let's find the line that's as close as possible. When we talk about closeness using least squares, we're talking about the sum of squared errors or how far the squared distance of the residuals is. But when you get into more and more advanced models for those continuing to 346, you'll change it from least squares to other functions that you'll be minimizing, okay? It'll be some combination of calculus and R doing it for you, depending on the particular instructor. But the idea here is that least squares line is optimal given the data, in the sense that this line is the closest line we can fit to the data if we take closeness to mean the sum of the squared distances between the point and the line. There's other measures and there's other applications, but we're going to understand this one first. We're going to talk about generating fitted values from a regression. And we talked a little bit last lecture about the connection between the regression coefficient and the correlation. They're closely related, as you might suspect. The reason we do that is because that all the intuitions we built up earlier in the course about when is the correlation causal, what sorts of fallacies can we make with it, all the intuitions we've built up about those sorts of things are going to carry through to the regression. And we're going to carry those with us through the rest of the course, okay? So don't lose any of the intuitions from the first part of the course. Interpretation and misinterpretation of regressions. We'll talk about how to interpret them, and we'll start off with the line with the competency study, of different candidates. We'll start out there again, finish that example off, then we're going to turn to extrapolation and causal misattribution. The idea of extrapolation, which we'll get into, is that if you fit a line to some data, you can make claims over the range of the data, but if you go too far off the data, weird things can happen. I'll give you an example. Another one is causal misattribution. Just because you can fit a line to data doesn't mean that X causes Y. And this is one of the big things I want you to get from the course, to separate when you're making a descriptive claim from when you're making a causal claim. The last topic we're going to talk about is regression to the mean, because every year or two, you see it show up in a published paper where the author claims to have found a particular empirical pattern in the data, when in actuality, it's regression to the mean. This also has deep historical roots in our field. Okay, so starting with the linear regression model, just to talk a little bit about the anatomy of the model. We're going to denote the outcome as yi, all right? And we're going to reserve yi to mean the outcome. Alpha is going to be the intercept, beta is going to be the slope, And epsilon or E, which one do we have? Epsilon I. We'll use either epsilon I or EI for the error terms. Those letters are reserved for these purposes. Given a value of X, the model predicts the expected value of Y if we assume a linear relationship, okay? And that's what we're gonna use this for. So how is this going to work in practice? The interpretation of beta is the average increase in the predicted value yi given an increase in xi. If folks, do they still teach like y equals mx plus b in school? Right, yeah. Congratulations, you've graduated to college. Now we put an error term on the end. But all the same intuitions carry through in that it's a slope exactly as you've learned what a slope is, okay? It's the expected increase in yi it's the expected increase in the predicted value of yi if xi were to go up 1 unit. And that's how we need to interpret the slope coefficient. It's literally, sometimes it's called a marginal effect. What's the increase, what's the effect on the predicted value if I move xi up 1 unit? That's what beta's answering. So with the linear model, the sort of claims we'll be making are, on average over the data, larger values of xi are associated with larger values of yi. And a 1 unit increase in xi is going to increase our predicted value of yi by beta, or beta hat. The expected value is the average outcome given xi. So this means if I were to tell you what xi was, here's what I expect it to be in the answers. Here's what I expect yi to be, and that's going to be alpha plus beta xi. The point estimate, recall that the alpha and the beta are the true slope, the true interceptance slope that we never see. Alpha hat and beta hat are functions of the data. That's the estimated intercept and estimated slope. We're going to walk through all of this in a few examples. So the key issues to take away on this particular slide are that that alpha plus beta xi is the expected value, and the point estimate is alpha hat plus beta hat xi, which is a function of our data. Okay, the expected value is a function of our model. The point estimate is a function of our data. When you enter this into R and you use the LM function for linear model, it's going to give you an intercept and a slope. That's going to be the alpha hat and the beta hat. All right, so let's work through one of these in an example. Just to refresh from the previous lecture, this is Russ Feingold and someone that Russ Feingold beat. And this study came out about 10 years ago, I believe. And it was rather jarring at the time in the sense that it argued that voters make their decisions based off the looks of a candidate, okay? And the effects that we're going to find from the experiment are non-trivial. To remind you of the experiment, respondents were asked to give pairwise assessments of how competent one candidate looked versus another. The treatment variable, or the independent variable, was how competent a candidate was perceived. The outcome variable was how many votes they actually got. Okay. Self-reflection for a moment. Has anyone ever voted for a candidate or against a candidate based on their looks? Consciously? No? Okay. The point of this article is that a lot of this happens subconsciously. Okay? And the effects are non-trivial. So let's first take a look at the R output. This is the, when you take their data and you enter it into R, this is the output that you'll see, okay? We're gonna go through, and I just wanna explain this and the parts of the tables that we'll be using. The difference is the difference in the electoral vote, the vote percentage for the candidate, and COMP is the variable of how competent they are. And we just stored it in a data frame called data, okay? So the first thing, the call just tells you what was entered into R. The residuals, we literally never use this, but we'll talk about some graphical diagnostics that serve better than here. This down here is the regression table, and this is what we will be using. We're going to focus in this lecture, not on coefficients, on the estimates, this first column. So this intercept column is going to be alpha hat, and this is going to be beta hat. So the intercept is negative 38.399, and the competency, the slope is 77.465. As the course progresses, we'll work through this column, this column, and this column. But for now, we're going to focus, and actually this part at the bottom as well. But for right now, we're just going to focus on this number and this number. So let's talk about how this number was constructed. We give to R a designated outcome variable, which is the difference in vote share for each candidate. That's going to be our yi for each candidate. Okay, how many observations were there? 95. Okay. Then what we're going to do is we're going to have an x variable, which is on a 0 to 1 scale, what proportion of the time that person was deemed more competent. 0 being they just look totally incompetent, 1 meaning they're wildly well put together, generated from those pairwise comparisons. Each candidate then has 2 numbers associated with them, a difference in vote share and a measure of competency. And we want to know if we fit a line to that data, what's the slope in competency? A 1 unit move in competency leads to what change in vote share? If we use the method of least squares, which means we find the line that's closest to the data, that's the slope and intercept we get. Negative 38.399 and 77.465. R does this for you. So I will not be asking you to do this manually. It just comes out of the computer, right? But I do want you to understand how these numbers are generated. These numbers are generated by assuming a line alpha plus beta x and finding the line alpha plus beta x that's closest to y. In the method we described in the previous slide, if you can get some calculus to get there, you can work with parabolas. There's a couple different ways to get there. But these are the estimates that minimize the residual sum of squares. So given our data, this is the best possible line we can come up with. Let's talk about what this line is saying. If someone looks totally incompetent, okay, someone suggested Boris Johnson the other day. Okay, fine. Let's say Boris Johnson is just a 0 on looking competent. Do folks know Boris Johnson? Okay. Let's just say he's a 0 on looking competent. Then if he were to run in a US race, we'd expect him to lose by 38 points. Okay? Or 38.399 points. How do I know that? Well, I plugged in a 0 for competency, so I'm left with the intercept. So the intercept is telling us the expected value or estimate of the expected value of the outcome if the independent variable is set to 0. Right? So if I set the independent variable to 0, then I expect the person to lose by 38 percentage points. That's pretty bad. Now, let's go in the other direction. Let's imagine that the person, everyone thinks this person looks competent. Okay? Did we end up with someone who looks totally competent? Ideally a politician. Obama. Fair enough, right? So let's say everyone agrees, love him, hate him, whatnot, he appears competent when you look at him, right? So if someone was always perceived as looking competent, then what we do is we'd expect them to win by negative 38 plus 77. Okay, because we're going to put a 1 in for competency. and leave the intercept in. So that's going to give us an estimate of what? 39 percentage points. Did I get that right? Mental math moment. It's not always the best to do that in front of crowds. So at that point, if someone looks totally competent, we'd expect them to win by 39 percentage points. If they look totally incompetent, we'd expect them to lose by 38 percentage points. Do folks see where those calculations come from? We'll go through a few more examples of this as we move through the course, but it's upward sloping. One takeaway from this is when you talk about these results in your JPs and your senior theses, you don't want to imagine moving someone from looking like Boris Johnson to looking like Obama. That's just, right, huge. Instead, what you want to do is say a 1 percentage point increase in appearing competent leads to a 0.7 percentage point increase in vote share. So the 1 percentage point, so I'm saying rather than moving up 0 to 1, let's just move 1 percentage point. That's going to take the slope 77 and divide it by 100. So that's 0.77 percentage points. And that's a little bit more reasonable, right? That's just saying go buy a suit and have a tailor handle it if you're a fellow. I don't know anything about women's clothing, but like do what you need to do there, get a haircut, like all those sorts of things. And you might be able to eke out within a percentage point or two just from appearance alone. All right, that's the interpretation of this. When you're running a regression with two variables, it's always important to plot the data and include a plot like this. We'll get to the dashed lines a little later. Those are standard error and confidence interval lines. But for now, let's just focus on that solid line, which is the line of best fit to the data. So looking at this, looking at the data from the original study, does it look strongly linear? Not really. I mean, there's a noticeable positive trend to it. But just as importantly, it doesn't look quadratic or anything, right? Like a line is as good as anything else to fit to this data. And what this conveys is what the data looks like, but it also shows you like, if exactly half the people, if your competency assessment is at 50%, or 0.5, then you have no real gain in predicted vote share, right? And we can get all this from analyzing the line, and this is where the results, and this is how the results were presented. Okay, any questions on this particular study before we move along to the next one? We're going to continue to use lines first as a descriptive tool, and then we'll start using them as an inferential tool after we build out a few ideas of inference. This was an absolutely fascinating paper from a professor down in at Baylor, which is in Texas. Okay. And what I liked about this paper is that it treated, I'm trained in a particular branch of political economy and trained to think in a certain institutional way that views everything as arising from material concerns. So people have ideologies, but the ideologies just reflect underlying material concerns, just the distribution of stuff in the economy, distribution of goods and that sort of thing. People have ideologies, people have, you know, whatnot. And this traces this traces all the way back to Marx. But the idea that people's ideologies and identities and so forth are actually epiphenomenal. They're just not, they're not essential. They're driven by underlying material interests. Okay? Take that supposition or leave it, but that's at least where I've come from things, right? Like if I ever see someone's ideology, I look for underlying class concerns, underlying distributional concerns, that sort of thing. What I liked about this paper is that it actually treated, in this case, Christian practice as itself important and a causal variable, okay? And there was an entire literature, it was really, really fascinating, on Protestantism and the capitalist work ethic. It was started by, I believe, Max Weber, and there have been a couple of, I think Thorsten Veblen was in it, but it was like an early 20th century vein of literature that was asking, is there a relationship between being Protestant and capitalism emerging? Or vice versa, right? I mean, if you go look in the Netherlands, both happened at the same time. Or is there a relationship between being capitalist and Protestantism emerging? The problem with that sort of analysis is that there's no real natural experiment, clear causal variable. Is one driving the other driving one, both being driven by something else? It's just impossible to disentangle. So this paper took a different approach. And what it did was it compared how the level of Protestant versus Catholic missionaries related to the levels of democracy in areas that they colonized. All right? And none of this is an endorsement of colonialism. This is entirely a natural experiment. So the idea behind this, I was raised in a Catholic church. I had to leave for reasons. I've been a practicing Presbyterian. The Catholic Church is notorious for just telling you what the answers are. Right? Like, oh, what's happening? Oh, the Pope said, and then he tells the cardinals tell the bishops tell the priests, and the priests tell you, and that's what the Bible says. Okay, thank you. And it's a very hierarchical structure. The Presbyterian Church, at least, and I believe Protestant churches in general, are more open to the idea of talking about things. I was a bit taken aback at a meeting after church where they're like, we're going to decide what we think about this particular issue. And I'm like, don't we have people telling us things? And they're like, not in this denomination. And the idea, and I think the stylized fact that Woodbury picked up on is that in the Christian faith, Protestants are more open to talking about things than Catholics are, to debate and, debating and self-organizing. The obvious implication that he drew from this was, well, maybe having Protestant missionaries instead of Catholic missionaries inculcates ideas of constructive debate and civic participation that lends itself to stable democracy. Do I necessarily buy that argument without data? Not really, but at least it's plausible. It at least rings true to me. It doesn't ring true, it rings plausible to me. And this is what he ended up looking at in the data. So we're going to take a look at his data and look at the relationship between the number of Protestant missionaries in a country and its level of democracy today. The first figure we're going to look at is just Protestants versus Catholics on the left and on the right. And if you read his paper, he does a slightly more complex analysis, but we're going to get the basic ideas out of it. Looking at the left and the right, I put the line of best fit in for each. The democracy measure runs from 0 to 100. And then the x-axis is the log number of missionaries in thousands. So do either of those look horribly linear? Would you look at either of those and go, yes, a line? No. He goes through and isolates a line, and that's an effect and that sort of thing. But let's take the data and break it down a little bit by region. Okay? And we're hitting that same problem that we hit with the disaster relief aid, where when you break it down by region, in that case it was by election, but here it's by region, you start to get a clearer picture of the effects. Whenever you're looking at data before you start running regressions and things, look at your data. Plot it, get a sense for what relationships might be in it. Looking at these, do any of these, if we break it down by continent, do we start to see any plausible linear relationships in some of them? Just give me one that you might see. Latin America looks like it might have a relationship, right? I might spot you Mideast North Africa as a maybe. Sub-Saharan Africa is just being driven by a couple, but maybe. And Asia has a huge cluster. Again, at least this is more suggestive, and at least more suggestive of a positive relationship than the last slide that put them all together, right? And importantly, all the lines are going up at roughly the same level. They're all unambiguously sloping upwards, which is what his theory suggested. The more Protestant missionaries in a country, the higher the level of democracy today. Again, not conclusive, but at least there's something suggestive, and I hope I've sold you that there's something suggestive happening. An important part of every theory is something called a scope condition. A scope condition defines the bounds where you expect your theory to hold. So the idea of a scope condition is it says, in this condition, I expect to see my effect, and in this condition, I don't. And by clearly delineating when you see a condition, when you expect to see a condition and when you don't, it can help strengthen your argument. Because then what you can do is look for a relationship where you expect to see it, and then not find it where you don't expect to see it. To give an example here, this effect could be driven entirely by missionaries or entirely by Protestantism, and we don't know. It could just be that more missionaries are doing it. Your question. Mm-hmm.
Like the slope is very high, but like you can.
Yes.
Like that's not like a real function that I'm like looking at.
Yes. So, yes, so you're being appropriately skeptical going, well, if I can put a line to anything, then I'm going to find effects everywhere, right? That's exactly the right approach. We're going to build out a sense of when we can distinguish these sorts of slopes from noise. We're not doing that yet. If you can trust me that some of these are distinguishable from noise. All right? You'll spot me at least the Latin American one.
Yeah.
Okay. So what this would say is that what the author needs to do and what the author does in the study, and I believe he had a subsequent book, is he does a historical study of each of these areas and relays different mechanisms and explains why the effect might be more pronounced in Latin America than Asia. Because there's entirely different dynamics underlying every one of these. But the point that I would like to forefront that you made that was absolutely correct is that we can put lines to anything and tell stories. Let's not do that casually, right? So we will build out that machinery. So with the scope conditions, his scope conditions in this study are that there should be a positive relationship between number of Protestant missionaries and the level of democracy today. What does this theory say about Catholicism, Catholic missionaries? There should be either a flat or no effect, right? So the scope condition here is that we expect it to hold for Protestant. We expect this relationship to be positive for Protestant missionaries, and up to the appropriate skepticism, absolutely appropriate skepticism, at least the lines are upward sloping, then we wouldn't expect to see this relationship with Catholics. Let's look at the relationship amongst Catholic missionaries. It's more of a mixed bag. The critiques of the Protestant data carry through here. All these lines could be noise just as much as the others. But you are finding that similar relationship in Latin America. So it seems that in Latin America, the level of democracy today correlates more with number of missionaries than Protestantism rather than Catholicism. It's just number of missionaries. But in sub-Saharan Africa, you start to get a different slope entirely. Looking at these two data sets, it's at least vaguely suggestive that there is an effect for Protestants, but there might also be an effect for number of missionaries total. And I want to highlight the scope condition idea that we expect to see the relationship with Protestants, but not Catholics, and you want to do both in your study. It's not just, here's my hypothesis, I expect to see an effect over there, and then you go find it over there. You also need to say, I don't expect to see an effect over there, and you show it's not present over there. And that helps to show that your mechanism is actually at work. In pushing this sort of thing forwards, this sort of analysis, you can't randomly assign 17th century missionaries to non-European parts of the world. Okay, that's kind of like done in history. The two different tracks that scholars have been taking recently in this area, the first one comes from this paper, where you use this data for a particular role in your argument, but it's not the main piece of argument. This is more to establish some sort of face validity, like, oh, hey, this might actually be happening. The data doesn't contradict my story, okay? It doesn't show my mechanism is there, I'd have to randomize or something, but at least this is consistent with my argument. Then you go back and you do historical work, archival work, qualitative work, go back to journals and articles, and like you really build out a qualitative story in which this is a singular piece. The second sort of argument that you can make is much more qualitative, is built based off natural experiments, where what you can do is within a country, you can compare areas where missionaries settled versus didn't settle. And one of my colleagues has done this in West Africa. Where if you go back to the diaries of the settlers at the time, they're meandering in a certain way through West Africa. They're just European colonizers. They have no idea where they are or what they're doing. They know why they're doing it, but they don't know where to go. And various weather patterns or a brush, too much brush or a fire or something randomly sends them one way versus another. So you can compare areas where they settled versus areas where they didn't, and find effects on educational attainment and income even through to today. All right. The problem with that approach is not only is it much harder, but you're reliant on finding these natural experiments and them having existed. This argument treats it more as a qualitative piece that you're building out. This treats it as a piece of a qualitative argument. The other one treats it as a natural experiment. Both come with their pluses and minuses, but I want to alert you to both strategies. Oh, okay. We'll revisit this one a little bit later. But we're going to talk about the number of daughters a legislator has and their score as they're scored by the National Organization of Women. Okay. This is a now famous study that came out in the American Economic Review in 2010. Abanya Washington, an economist at Yale, did it. And did we talk about how special interest groups will score legislators? Special interest groups will score legislators. The NRA will say, here are the 8 bills we care about, or the 50 bills we care about, and give each legislator a score normally normalized from 0 to 100, so that you can show your score this year based off the NRA, right? So your lifetime rating score for the NRA might be 100% if you're from Texas, and it might be 0% if you're from New Jersey, maybe. Really, really high if you're Bernie Sanders, by the way. And then this study comes from a scoring done by the National Organization of Women. The author, Abanya Washington, argued that the scoring by the National Organization of Women was a measure of how feminist a legislator was or how they supported feminist issues. Not going to get into that particular leap that she made, but I will say it's a scoring by the National Organization of Women. The scoring ranks from 0 to 100, and the question she asked is, were legislators that had more daughters more supportive of the National Organization of Women? The idea here being that having more daughters in your house just makes you more sensitive to the concerns of girls as they're being raised, and just makes you more aware of these issues, and it gives you a personal stake in these issues. So we're going to look at just 2 variables from her data set. We'll build this out a little bit later. The outcome YI is a 0 to 100 scale. There were 20 bills that the National Organization of Women decided to score that year. So scores range from 0 to 100 in intervals of 5. And then XI, the independent variable, is the number of daughters that a legislator has. So let's look at the output from this regression. We're going to look at 430 legislators. In this particular Congress, there were 435, but every year there's a few who die, are indicted, just leave for various reasons. So there were 430 that were there for the entire term and scored by the National Organization of Women in the US House. And the relationship we get is 44.14 minus 2.15. Okay, so let's interpret this. Our fitted value for the score from the National Organization of Women is Y hat, which is going to be alpha hat plus beta hat times the number of daughters. Looking at it briefly, and there's a couple examples of this below. If someone has no daughters, if a legislator has no daughters, we'd expect the National Organization of Women to score them at about 44.14. Right, that's just setting the slope term to 0. If someone has one daughter, then we'd expect them to score 41.99. So the addition of each, so by adding another daughter, we predict that the US House member would be less supportive of issues supported by the National Organization of Women. Does that pass anybody's, I see people going, huh? Does this pass anybody's sniff test? Does having more daughters make you go, ugh? No. Yes. The problem with teaching with such a large group is that someone ruins the punchline for 4 lectures from now. So thank you. That's what's going on. We'll talk about it. When we talk about putting more variables in, when you start to include variables to adjust for whether someone's Democrat or Republican, the effect attenuates some, it moves closer to 0. After you put in total number of children, it starts to go up. And then you also had that precept discussion with the Glynn and Sen data, right? Where it was there's multiple ways to get more daughters, you can get more children, or one of your sons could have been counterfactually born a daughter. And Abanya Washington was interested in the counterfactual shift, but you need to create a specific model to accommodate total number of children. All right, so thank you, sort of. But from this particular model, the estimated marginal effect is minus 2.15, which just says that we'd expect a legislator with one more daughter to support now by 2.15 percentage points less. The takeaway from this is that be careful. You can end up with weird results if you don't model properly. And if you find something that seems counterintuitive like this, because you could stop here with this result and stand here and go like, and just say all sorts of weird things that aren't true, right? Don't do that. Interrogate your model, interrogate your common sense. If something seems countersensical or contra your common sense, interrogate the model, interrogate the data, make sure it actually holds. Have we eliminated alternative stories? Have we correctly isolated a random fluctuation? The sorts of things we're talking about here. Could there be other variables driving it? That's all part of the conversation. One problem I want to talk about is the problem of extrapolation, which says that because technically we're fitting a line that could just include everything, right? This line allows us to make claims like if someone had 50 daughters, we'd expect now to give them a negative score of negative 63.6. Now doesn't give out negative scores, and 50 daughters, that's hard to imagine. Maybe, who was it, Genghis Khan maybe? I'm trying to think of like who hit that level. What's that? Genghis Khan would have a negative score as marked by the National Organization of Women. Touche. So then, you could also say things like, well, what if someone has negative 3 daughters? I don't even know what that means. And the line is going to run through places that don't always make sense. Of course, in this setting, you don't want to talk about someone having negative 3 daughters. But there was a study that was talking about, and I think this came out in Science, arguing that there'd be a momentous sprint at the 2156 Olympics where male runners, the male races are always male runners. The fastest male runners are faster than the fastest female runners. Okay, and that's just the case in all the different Olympic events. This study came along and argued that at 2156, women would catch up with men. Here's their data. They were looking at the increase. The red is for women and the blue is for men. And they were looking at the fastest time by year from 1900 through to 2010 or so. And you see that downwards progression, right? Like the winning time for men is sloping downwards linearly. The winning time for females is sloping downwards linearly, but more quickly. to the point now where the fastest women today would have beaten the fastest men in 1900 or 1910. And in fact, in 2156, we expect the lines to connect. Oh my God. So does this ring true as the sort of thing we should be doing with data? No, right? Like first off, global warming is happening, right? Like God only knows what's going to be here in 2156, he says morbidly. But at the same, yeah, that was an uncomfortable laughter. But the point I want to take statistically is we don't want to go off our data. When we talk about lines, we want to talk about the linear relationship within the context of the data we see, and maybe a little bit outside, but certainly not 150 years. So one of the problems is you could actually fit different models to this data that seem to fit equally well, right? If you calculate how close those two lines are, they're both equally as far from the data as the earlier line. The result in this paper was driven entirely by the linearity assumption rather than any understanding of how these lines are actually progressing. If you want to play this game, you can go like that. And go like, after the year 2085, men are going to start getting slower. Women will start getting slower around 2040 and just angle up to the point where in 2150, we'll just all be so slow that, I mean, like, you know, the game that they played with the lines, I want to capture a bit of skepticism here and say, when you go that far off the data, you have nothing supporting your claims. So if you're going to draw a line through the data, I can draw another line through the data or another curve. Question? That varies on the context, and there's exactly 10 seconds left. So I will try and lead with that after the quiz or send me an email, because there's concerns we're going to come to of, well, if it's not linear, what is it? But I will see you all for the quiz on Thursday. Excellent question, though.